A Reranker does not need to score everything. A Cascade keeps quality where it matters and saves ONNX calls where it does not. This is the pattern you'll be able to implement by the end, which ranks candidates, then escalates uncertain scores. I'm Professor Pi, teaching search and IR with simple Python. Start with the practical pain. At search scale, you often get dozens or hundreds of candidates from a fast index. A deep cross-encoder can make much better ranking decisions. But that model is expensive and slow when called for every candidate. Reranker Cascades solve that by using a cheap first pass to handle most queries and an expensive second pass only when the cheap pass is unsure. The goal is faster end-to-end latency with minimal loss in ranking quality. ONNX Runtime is the engine we use to run the expensive model. ONNX Runtime is a runtime that executes models exported to the ONNX format, so you get optimized inference across CPUs and GPUs without rebuilding your model code. For this pattern, ONNX Runtime is a good fit because it loads a compact serialized model quickly and scores small batches faster than many full framework setups. Think of it this way. You have a short list of candidate documents for each query. The cheap stage is a fast heuristic that orders them roughly right. The expensive stage is a learned cross-encoder that can untangle subtle signals. If the cheap stage shows a clear winner, we skip the heavy model. If it shows a tie or close call, we run the expensive model for just those uncertain candidates. This saves compute while keeping high quality where it matters. We will build a tiny end-to-end demo. It shows a lexical cheap stage, a simple uncertainty test, a tiny ONNX linear model as the cross-encoder, and a final blend that prefers the cross scores only for the ambiguous items. You will see how the pieces connect and why each decision exists before any heavy code. Quick note, this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. Now we need a first baseline to inspect. The cheap stage should be simple and transparent so we can see what it gets right and where it fails. This snippet picks a starting document by counting query term hits across a tiny candidate set. The list docs holds 3 short retrieval candidates, so you can easily watch what happens. Query terms tokenizes the request, and the hits comprehension tallies Boolean matches per document to give a clear, interpretable relevance proxy. Max then chooses the document with the highest hit count, and the printed baseline doc shows which candidate leads with 2 matches, the one the cross-encoder needs to beat. The raw counts show bias toward longer documents, so we normalize to make scores comparable across different lengths. This example turns raw hit counts into a normalized signal, so different document lengths don't dominate the cheap ranking. Cheap scores computes the match token ratio by dividing matches by doc length, making the scores proportions that blend sensibly with other signals later. Sorted pulls the top 2 into cheap top, and first names extracts their leading tokens, so the shortlist stays human readable while debugging. The printed cheap stage list and best signal demonstrate that Rerank still favors a 0.29 normalized hit rate, which explains why that document remains in play. Even with normalized hits, we still need a way to detect when the cheap stage is uncertain. A small margin can signal when to call the heavy model. This code detects when the cheap stage is too close to call and prepares richer features for the cross-encoder. Cheap signal map makes the normalized scores easy to look up. Margin computes the gap between the top 2 signals, and comparing it to the 0.18 threshold decides whether both candidates are uncertain. Pair features then builds compact vectors coverage, latency flag, and cross-term density, so the expensive model gets more nuanced inputs than raw counts. If you lower the threshold, the Cascade calls the heavy model less often. With the current margin at 0.16, the printed summary shows both items still need cross-encoder attention. Next, we need to run an expensive model for only the uncertain items. To keep the demo simple, we build a tiny ONNX linear model and load it directly into memory with ONNX Runtime. This snippet constructs a minimal linear ONNX graph and loads it into ONNX Runtime so we can score small feature batches quickly. Helper.makeModel creates a gem node with weight and bias initializers to score 3-element feature vectors via a single matrix multiply. And ORT inference session consumes the serialized model bytes in memory to keep setup light for experimentation. Converting uncertain docs into a NumPy array confirms the batch shape is correct, and the print verifies one ONNX input is ready, while 2 documents await scoring. With the cross-model ready, we evaluate only the ambiguous items and then blend those logits back into the full ranking. This example runs the Cascade end-to-end by scoring only the uncertain items and merging those logits with the cheap signals. Feature matrix collects the pair features vectors for the ambiguous docs, and the conditional cross-session.run call prevents unnecessary work when the cheap stage is decisive. The dict comprehension rebuilds Cascade scores, so cross scores override only the ambiguous candidates, while the rest keep their normalized shortcuts. Sorting the blended scores promotes whichever document the cross-encoder prefers, and the printed Cascade doc shows the latency-focused candidate now leads, with a 1.45 score. In a real system, this tiny demo maps directly to production components. The cheap stage becomes a lexical filter or vector approximate nearest neighbor shortlist. The uncertainty threshold becomes a routing rule in your inference service. The ONNX model can be swapped for a larger cross-encoder and deployed on a GPU-backed inference node for lower tail latency. This pattern gives you a clear lever. Cheap filters handle the easy cases, and the heavy model only resolves the close calls. Use it when you want most queries fast and only a few to hit the expensive score. Pick the threshold with care. It's the knob that trades compute for ranking fidelity. Next step, tune the uncertainty margin and measure latency and ranking changes to find the sweet spot for your traffic and model. If short, practical IR helps, subscribe and watch the IR videos.